Good evening. Thank you for joining us on this rather late session. I hope you're not too tired or getting hungry or hangry. So we'll try to give a good presentation to keep you awake. It's about half an hour. And we're going to talk about a project that we did on outsmarting the grid with AI. My name is Peter Defreyne. I'm here together with my colleague Martijn, and we are from Ixor. I'm just going to start out with just a bit of context. The project is in the context of energy management, which used to be really simple. I think many of you will know what this device is. It's just an analog meter of your electricity consumption. It's actually the advanced one. It has a day counter and a night counter, but that's it really. You don't need to think about it. It's just a number that counts up. And at the end of the year, you need to pay the amount that you have used. If you have solar panels, then it will just wind back if you're not using the power. So again, you don't really need to think about it. Energy management used to be easy. This is no longer the case. Many of you will now already have a smart meter or a digital meter. And actually, instead of a counter, you have a time series data of your energy consumption. It looks a bit like this. It's really detailed, the data that's being captured, but it's constantly being monitored when you are using energy, how much energy you are using, the amount of power you are drawing from the network at any given point. And also separately, now you can see the green bars, the amount of solar power that you have been giving back to the grid. You're now getting paid less for this power. So again, this is already something that's changing, that's becoming more difficult. You want to consume the electricity you generate rather than inject it in the grid. Other things have changed as well. There's now a thing called the capacity tariff. You don't just pay for the amount of power that you use, but also how much power you have been using at any given time. So if you plug in your car and you don't manage it, it will draw a lot of power. And this peak, you will pay for it for the entire month, even if you just use it for 15 minutes. So again, more complexity that's being added to your energy management at home. On top of that, we used to have single tariffs on the left, a flat line. We have day and night tariffs, which many of you will know. But now there's also an option to have dynamic tariffs, where every hour there's a different tariff. And you feel, okay, if you can use the energy when it's cheap or even negative, there's a deal to be had. But on the other hand, if you don't deal with it properly, it can end up costing you even more. So again, more complexity that's related to your energy management. Your house is also getting smarter, more complex. Many people have invested in a home battery to buffer the solar power and to give the power back at night or in the evening. Again, another element in the building, many of you will probably have an electric car or a hybrid car. It's another consumer, which we didn't have in the past, and now we do have it in our building, and it's consuming a lot of power. It can end up doubling or even tripling your normal electricity usage compared to just a normal usage. Same for heating. Many of you will have a heat pump. Again, it will be using a lot of electricity, which before it didn't do. So another big consumer that's within your building. So energy management used to be easy. Now it's really complex. There's a lot of devices. There's new consumers. You're being taxed or you need to pay in a different way. And if you don't take into account these changes, then you will end up paying a lot of money for your energy. So you want to manage this. You want to take control over it. But you don't want to do it as an end user, as a human. You can't just keep on scrolling continuously on your phone what's happening to try and steer. You need a system that can do it for you. And this is something it's called an energy management system. For the home, it monitors the energy in your home, the flows, and it will try to adapt these flows for you. So it integrates with your car charger, your heat pump, perhaps your home battery, your smart meter, and it will monitor all the flows, the energy flows in your building, and it will try to alter them if required. So using this real-time data, It's going to do peak shaving, for example. If you consume too much electricity, it will slow down the charger. If you have solar injection, perhaps it will turn on the boost function of your heat pump, so it will try to optimize your energy usage for you, which is good, but it's not enough. And that's, well, this is a solution our customer has built, and we try to make it better for our customer, because this device doesn't know the future. It doesn't know what your power consumption is going to be in the near future. It doesn't know what the solar power will be that will be generated. It doesn't really know what your tariff or your energy contract is. It doesn't know whether it's smart to charge a bit sooner or rather later, and on what basis it should decide this. And it also can't tell you whether your car is going to be charged in the evening the way you've asked the system to do it. There's no guarantees in the system anywhere. So we tried to solve this, and the way we did it is using the energy data, because there's a lot of data available. All these energy consumers are becoming IoT devices. We can look into them. We can know what they're consuming. But still, it's a lot of data, and it's really messy data. This is just an example from my home. You can see some appliances that are causing spikes. You can see my car that has been charging. You can see the green graph. It was a sunny day, so you can see there's a lot of energy being generated. You can see my battery charging, discharging. And so there's a lot of noise in the data, and a lot of this data is not managed. It's something that just gets summed up and piled together, and you need to deal with it somehow. So that's a challenge. A second challenge is just me as an end user. I have a lot of conflicting requirements, because suppose I want to charge my car for an additional 50 kilometers of range. So that's the first requirement. But I want it to be done as cheap as possible. That's the second one. A third one is, don't cause high peaks in my consumption, because I will end up paying for them. So that's another one. I want to use as much of the solar power as I can and put it into my car rather than inject it. So yet another requirement. And I might have a deadline when I need to leave, when I need this range in my car. So these are really conflicting requirements. And it becomes really hard to just create an algorithm to calculate the correct solution on how to deal with this, because there's no real correct solution. There's just an optimization problem that needs to be solved, rather than some logic that you can apply that will always give you the right answer. So there are two challenges. The first one is, we need to forecast. We need to predict the future somehow. And on the other hand, we need to find an optimal solution for my very conflicting requirements within my home. We've tried to solve this, and the solution that we've built, we've called it EOS, or the Energy Optimizing Service. Not very creative, I know, but it acts like an additional cloud service on top of the energy management system. So it still runs autonomously, but all the data is being synced into the cloud and stored. So we have, on the left side, we have real-time data, we have historic data, and we add or enhance it with a lot of data that has some predictive power, such as the day of the week. Is it a working day? Is it the weekend day? What's the weather going to be like? Where do you live? What's the coordinates of where you live? What's the forecast of the weather actually going to be there? So a lot of parameters that have some predictive value. Also, what's the dynamic pricing of the tariffs going to do? All this data, we add it together and we get to work with it. So this service, it does three things, basically. It will forecast. It will forecast your consumption. It will forecast your production, the solar power, and it will generate an optimal schedule for your heat pump, your car, your home battery, and any other large consumer that we can manage. So it will generate an optimal schedule that can be executed by the energy management system, and we will monitor it and continuously improve it to keep the target feasible. For example, me charging my car with a certain deadline. Before we dive into how we did it and which tools and solutions we used, we thought it might be best to just try and show you how the solution works. So Martijn will do.
Yes, I will take over now. So let's start with the most exciting part, maybe. So live demo. Also a little bit risky, I think, but okay. So here you can see user interface we have built. This is not what the end user sees. It's just something we built for ourselves as developers to play with the parameters and see what the output is. So we have put in some parameters, and let's compute a schedule. So to go over it, you can see the parameters. For example, the maximum peak, we can set it. We can say the number of EVs we have, how much energy is needed for that EV, how much hours we give it to charge, and also some other parameters. And here we can see the output. On the top, we see the pricing. So for this user, he has a double tariff, so a high price during the day and a cheaper price during the night. Then below that, we can see the forecast. So the forecast here in the beginning, you can see it's negative, meaning there's excess energy predicted for this household. So this is energy we actually can use to charge a car for free. Below this is also some extra information, the weather parameters we get for this user, indicating the amount of energy we can expect from the sun. And here on the bottom, we can see the schedule that has been created for the car. And as we can see, it starts by using the solar energy that is predicted. And then it sees, okay, all the solar energy is used up. And then it moves some amount of the charging at night when it's cheaper. You can also play with the parameters. So let's perhaps add another electric vehicle. And let's give it maybe, let's say, 11 hours to charge. And let's see what it gives. So we have to wait a couple of seconds now. It's being computed in the cloud now. So let's wait one more second. Yes, okay. We got there. So now we can see the energy is distributed between the two vehicles. The one with the earliest deadline is being prioritized in the beginning, and then the other one also is given some amount of the energy. Okay, so that was it for the demo. Let's go back to the slides now. Okay. What we have built actually is a system in the cloud on AWS, and for the data part, we have created an event-driven architecture. And let's go over it real quick. So quickly go over the components that we used. So first, for compute, we use Lambda, which for people who don't know AWS Lambda, you can see it as something that executes your code in the cloud. You pay for it if it's doing something. If it's not doing something, you don't pay for it. So it's really flexible. For the database, we opted for DynamoDB. It's fast, reliable. It looks like NoSQL, and it's an offering from AWS themselves. Then for the event-driven architecture, we also used Event Bridge, which is also an offering from AWS, where we use the event bus. We use the event bus to throw events around, let's say. We also use the scheduler to schedule events at regular times. Okay, so how do we get all these different pieces of data in our system? So there's a couple of different sources of data. In our case, 3 mainly. So on the top, you can see the smart home device. That's one of the sources of data that we get. Then we also have a server somewhere that publishes the dynamic tariffs each day. Also, that's the second source of data. And for the weather forecast that we use to predict the solar prediction, we have some weather API that we use. So here you can see 3 types of data source. And how do we get this data in our database? Well, at some point in time, there appears some event on the event bus that says fetch some weather data. I will go into how it looks like, but for now, let's say some weather data appears, and then the event bus will pass it to the correct Lambda. The Lambda will turn on, connect to the API, and put the result in the database. Similarly, for energy data, you can say fetch some energy data. It will dispatch to the correct Lambda. It will do its thing and put it in the database. Okay. Then another thing we have built is this external services. They can fail. And how do we deal with this? Well, we have a separate service that regularly checks our database. It will check for missing data. If there's data missing, it will send an event to the event bus I talked about earlier, and will dispatch it to the correct data source Lambda. It will fetch the missing data and then fill it in. Okay, so let's continue. Okay, so these events, these jobs, where do we define this? How do we do this? So we have some pipeline that will where we define these jobs. And here you can see an example of it. So an example here you see energy meter data. You can specify how many times we want to get this data. Also the scope. So some types of data we want to get for each user. And some types of data are the same for all users. In this case, it's user specific. And there's also some other things we can specify. So we put this in the database. And we have two lambdas that are scheduled on regular intervals. So on top, we see the schedule lambda. It will be scheduled at regular intervals. And it will look in the database and it will look, okay, which kind of jobs are there? And then, for example, here it will see, okay, there is an energy meter job, and it will create a job for each user. And it will put it back in the database. Then, at the bottom, the other lambda will wake up at some point. It will look in the database, and it will fetch all the jobs. And then all the jobs are taken out of the database and put on the event bus, and the event bus will take care of the dispatching to the correct lambdas. Okay, so let's continue. Oh, what we see here. So, as Peter said, we collect user data, we store it somewhere in the cloud, on a database, and it's all fun, but at some point we have to deal with GDPR. And some part of the GDPR tells us that we cannot keep data indefinitely. And I want to highlight a cool feature, actually, of our database, and it's called DynamoDB time to live. So normally, to do this kind of thing, you would need a job that is run every day and checks for records that are too old. But if you use this feature, you can just add data, add a column that says, at this point, it has to be deleted, and then AWS just automatically deletes this record when it expires. So it's pretty cool feature, I think, because it just automatically helps us to deal with this stuff. Okay, so now let's get to the optimizing part, the forecasting part. And it's actually three types. We have three components. First of them being the scheduler. So how do we compute this optimization? So let's quickly go over the constraints that the scheduler has to deal with. So Peter already talked about this, but there's actually three constraints we have to deal with. So the pricing on top, the second thing is the capacity tariff, and the third thing is the planning, so the agenda of the customer. And here we see dynamic tariffs. So a naive scheduler would just start charging immediately, but here you can see it's the most expensive part of the day, and then we will pay a lot of money. Also for the capacity tariff, here we can charge a lot of energy at the same time, but again, this might cost a lot of money. So we want to stay below some thresholds that the user can set. And also, imagine we have multiple EVs. We want to be able to deal with the agenda that the customer set. So some EV might need to be finished before some hour, and another EV might have to be charged before another hour. And to do this, we need actually a really simple method. So there are many good optimization techniques out there, but through some trial and error, we discovered that we actually need a method that is consistent, predictable, and easy to work with. And that's how we ended up with constraint optimization. It's a pretty it's a pretty reliable way to do this, and it's been around for a long time. And it's pretty easy to work with, and I'm going to show now how we work with this. So let's imagine the capacity tariff ruling didn't exist. Then our scheduler would work like the diagram on the left. Then it would just use as much energy as possible, but the government may introduce this capacity tariff. And then we as developers would need to implement this, and with some techniques it might be pretty difficult to enforce this. However, with the technique we used, it's actually one or a couple of lines of code to add it to our model. So yeah, I'm going to quickly go over the expression here. So first of all, this is Python, and we use snake casing, so don't be angry at me, because I know Java uses scale casing. So basically, it's just a one-liner, and we compare the schedule with the peak, and we enforce that all the values have to be lower than this peak. And just adding this line to the model we have makes it work. So on the left, these lines of code were commented out. On the right, they were added, and the model adapts to it. Pretty cool. Okay, so we also need a forecaster to predict how much energy we're going to use during the day, because we need to know how many energy we can use. And for this, also, a pretty nice feature of the solution we came up with is that we have a model for each user, and also this model is being trained at inference time. So each time we create the schedule, we also create a new forecast. So some methods would train a model maybe each month or each year and then use it all the time. What we implemented is a method that always uses the latest data and is being updated at inference time. Yeah, let's go to the next one. So because we have one model for each user, we train it at inference time, we need a fast and lightweight model. It needs to be, we have one model per user, so it needs to be fast, and that's why we opted for light GBM. I don't know if everyone knows it, but it works kind of like a decision tree on steroids. It's developed by Microsoft, and I also think that explains the color theme here, so yeah. I'm not going to go into detail about this method, but it's a pretty cool technique. Okay, so the forecaster, it usually predicts one value. However, the forecast, we would want actually 24 values, one value for each hour of the day. So how do we do this? We have two methods to do this, a recursive technique and a direct technique. The image here shows the direct technique. And the recursive technique, it kind of works like ChatGPT. It creates a prediction, adds it to the input, and creates the next prediction, adds it again to the input, and so on. The direct technique, it actually trains 24 models. One model for the next hour, another model is trained for 2 hours, another model is trained for 3 hours, and so on. So that's how that works. Okay, so here's an example of how it works. So the blue lines is historical data, and the orange lines are the forecast that is created. So it looks pretty cool. So one thing to note about forecasts is that most of the time it's wrong, but in our case we need it to be the order of magnitude needs to be correct. we need to know if there's going to be energy in excess or if there's going to be no room for charging. And on the right, we also see other input data we use. So the blue and the red Dutch dashed lines, they show the solar forecast. Okay, so that was the forecaster we built. So all the technical things are pretty cool, but we also need to help the user for some things. And one thing we have is actually the capacity peak needs to be set by the user, but it's pretty vague, difficult to set this yourself. So we actually have a service for the user that simulates a whole month of schedules with different kind of peaks, and it will suggest the optimal peak. Then you can see on the right here what the effect is. So a low peak would, if you set a high peak, it will cost a lot of capacity tariff. If you lower it, it will be cheaper. However, if you set the peak too low, you're forced to spread over all the hours of the day. So on the top you can see two prices. And if the peak is really low, you have to spread the charging through all the hours of the day instead of focusing on only the cheap ones. And between these two things, there's some optimal value, and that's the one we suggest to the user. Okay. Another thing is, what is now the value of all these things? All these peak shaving, the smart scheduling, opting for a dynamic tariff instead of just a regular old simple tariff. And that's also something we simulate for the user and we give as feedback. So we help actually the user to compare the effect of choosing for one or the other option. That's actually one of the most difficult parts of the project, I think, is helping the user. Maybe now it's a great time to go back to you, Peter.
But just to wrap up, explaining what the algorithm does to the user is actually quite hard, because as a user you think in terms of range in kilometers of a car, temperature of a room, the cost of the energy bill. The typical user doesn't think in kilowatt or kilowatt hours. So that's still a challenge from a UX point of view. How do you explain these things to a user that it makes sense? And also the point at the bottom, explain the unexplainable. Yeah, it's a data optimization problem. Sometimes it suggests things that doesn't correspond with your gut feeling, but really is an optimal solution. You plug in your car, you want it to charge, and it doesn't charge. It's easy for an installer or a customer to think, oh, it's failing, it's not working. So there also you need a way to explain to your user that that there is a smarter way of doing it rather than starting the charge immediately. So there's still some work to be done. Finally, a last remark. We did it entirely in the cloud based on AWS. One of the requirements from the start was how much will it cost and will it fit into the business model of the customer? Because for this service, they want to charge a certain subscription cost per month. So we decided, we have some commercial requirements or targets. One is that, we want this solution to scale linearly per extra user, so not per server, per service, per Lambda, per whatever. Really per user, the cost should increase linearly. And the second is, the cost should be low enough that it fits within the business case. And because of the design choices that Martin explained, the Lambdas, the DynamoDB, the automatic deletion, the time to live of the data, we've taken this into account from the very start. And we see that at the moment we ended up at 1.2 euros per month for this service, where we run it basically every 15 minutes with retraining of the model and the inference runs. We think this is mission accomplished, basically. And that's, I think, all we have time for on the dot. But thank you for joining us on this late session.
All systems are nominal. Initialize Genesis sequence.